Oh yeah, it was just like a pentane ring or cyclopentane, and then
Mm-hmm.
on one of the carbons there was a methyl group. So
Okay, so it was, what was the reactant though, is what I'm wondering.
yeah, yeah, that was the reactant. It started out with the pentane with the methyl group attached, and then the next step was like the pentane with, and then on the same carbon, now there was the methyl and a bromine.
Okay, are you, this was one of the quizzes? This was the exam, on
The
the exam?
test,
On
yeah.
the test? Let me see if I can just view it so I know what you're talking about. Let's see. Mm. Preview. Okay, let me see. Mm.
Yeah, so it was
Mm.
like question 11. And
Oh, wait. Okay, yeah, hang on. It's because it's showing me because it was already closed. It's like showing me. Okay, sorry. I found it. So question 11. Okay, right here. So
yeah, step one.
this is why I can't see. Let me see. Let me take this off. There we go. Okay. So, yeah. So in the following synthesis, so it's asking you what the three
Yeah, can you
that
just
must be
explain?
done in the correct order, step one, two, and three, to obtain the desired product. Match the synthesis steps with the correct reagents. So this is a free
Yeah,
response question.
no, it's just a drop down menu.
Oh, it's a multiple choice drop down. Okay.
Yeah, so for step one, how do you
Yeah.
know if you're supposed to use the HBr or the BR2 in light?
Oh, I get what you're saying. I get what you're saying. Okay, so with this one, okay, so with the HBR versus, yeah, the one with light. Okay, I know this answer. Let me think what the specifics are. So it has to do with what it reacts. Um, I was gonna say, it makes an alkene an alkane, but that is not necessarily, um, because on this one we don't have a double bond. All right, let me see if
And
what's
the
going.
another option, the other option, the NBS was also lit and light. That was also a choice, I believe.
Yeah, what did you choose? You said, I thought that's what you
Wait,
said you chose.
no, I don't know. I chose something, then I didn't know, so I changed it. I don't even know what I went up with in the end.
So yeah, NBS with light versus HBR with its uh do they have NBS in here? I don't even see. NBS right here. Okay. So this is on page 94 versus what was the other option you said? HBR.
HBr and diatomic bromine too, with
Okay,
light.
yeah. Okay, okay, so we have 94 and then HBR is right here 46 and diatomic bromine is 16. So 16, 46 and 94. So 16, this will, on this one we just have a regular pentane. Um so the Hoffman rearrangement, that's for the amines. So bromine will react with alkenes, la 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 la. We read this. Finally, bromine is also used to promote the Hoffman rearrangement. So in the presence of light, bromine will also replace hydrogen atoms in alkanes. Um, see, I can remove alkanes because I just want to make sure. Okay, let me look at the next. Was it 46 and then 92 or something?
It was
Um,
46 and then 94.
Oh yeah, 94. Yeah, thank you. Okay, so in this one, oh Grignard, you guys are gonna get there. Um, yeah, so HBr you use, it has to be the alkane or alkene, excuse me. That's why it wouldn't be HBr. Because it
Oh,
has
wait,
to,
wait, wait, wait. It has to be that?
Yes, it has to react with some sort of, or in this case, right? You know, it can replace an alcohol, but we don't have an alcohol there. So because we end up making
Okay.
this a good leaving group, remember?
Yeah.
We end up with HBr, this takes on the H and then it kicks itself off and then Br can add on. So when we have alcohol, we can turn that into it's really what it is it's an addition addition like it's an elimination and then an addition reaction.
Yeah.
Because you add the hydrogen on, which makes this a good leaving group, and then it eliminates itself, right? And then the bromine adds itself on. So that's why we have this. It's basically replacing. It's not substitution, to be clear, but it's replacing it. But otherwise, you can see my screen, right? Where I'm
I
circling.
can, no, I
Okay.
can see it. Yeah.
Okay, cool. Okay, yeah. But otherwise, HBr, you would do it on the most substituted side of the, because it's Markovnikov, you know, so you do it on the most substituted cation of the double bond. So that's why it wouldn't be HBr, right? But there
Okay.
is a reason why the difference between, and I'm sorry it's not like coming to mind right away. That's why I just want to look at these, because there
Well,
is a reason why you use NBS.
yeah,
Definitely
I know.
NB
No, I
if
know
it's okay.
why.
Oh
Because
yeah.
it's just the thing about if you don't want um the substitution to take place on the double bond, you use NBS. But in this instance, there was
There
no
is
double
no,
bond.
yeah.
Exactly. So
Yeah,
then
that's
it's like, what do you pick? Because
how
they're
do
all,
you, yeah,
I
how would
don't
you
know.
decide the difference? So this is all NBS continued. So let's see, but there's no example without a double bond. I guess this would be, no, this is a continuation of that. Yeah, because that would be my thing. It would be like, yes, with MBS and light, it would have to do with the alkene, you know, is that you don't want it to react with the alkene. So what is it about the most substituted? Because it's basically, it's replacing like a hydrogen is leaving, but why? Because there's no
Yeah,
double bond there.
I don't know. And the reason why I was like kind of, I don't think I ended up going with HBR, but I want to say I changed it. But the thing with that one is the reason I was considering that is because the only like distinguishing feature of this I could find was that it's like it was substituted on the most substituted carbon, so I was like, it looks like Markovnikov, and I was like,
Yeah.
that was something I knew with
Yeah.
HBr, but then I was like, but then that also happens with the bromine. So
Yeah.
it's like,
Yeah. No, it does. It happens with,
so anyway, yeah, it's fine. I just,
that is
yeah.
very strange, right? Yeah, I don't know how to answer that question because, yeah, I would also be referencing the double bond. That's why I'm like, I, but yeah, you're right. The reason why is because it just has to do with not reacting with the alkene and you get it on a different carbon, but it's not, but that we don't have an alkene, which is why. How annoying, right? Let me see. Will this give us any hint as to why? No, because this again, it was.
Wait, actually, I think I just found it
Oh,
in
in the
the
gap
gap
notes?
notes.
What's it say?
Yeah, in the like first section of like the first part,
Hmm.
like literally the first example, it says it's the same thing, it just looks different. It's a pentane with the methyl, and it says
Oh,
Br2
yeah.
with light or NBS with light.
Yes, adds
And
to the
then it
most.
says radical bromination.
Yeah, radical bromination. Yeah, well, that's what radical bromination is when you have H nu. So synthesize the molecule on the right from the left. So the first reaction, at first, no, no, alkenes can be formed by elimination from either a halide. Okay, no, the first bromination is of an alkane. If we were brominating in an allelic position, only NBS could have been used. That is something I will say that I wanted to mention is it's a good habit to just use this when you're doing, rather than trying to remember the difference between these two, it's best just to get in the habit of using NBS and HNO because versus BR2 and HNO because you don't have to know the difference between the two, you know?
Yeah.
Like if it's allelic, then you have to use NBS and HNO,
Mm-hmm.
right? Versus if it's not. So if you just get in the habit of always just writing NBS and HNO. But yeah, yep. This involves a reaction of the multi-step. Yep. Then elimination. Halide water leaving group versus a water leaving as a leaving group. This is also good information to remember.
Mm-hmm.
This stuff right here, because all of this stuff is going to stay with you. Like the synthesis stuff is never going away. It's only going to get more and more complicated.
Yay.
I know.
Um,
Yeah,
yeah. Wait.
I was just trying to
Okay.
see if I could find the HNO, the photobromination thing. But yeah, go
Wait,
ahead.
can you? Yeah, I just like kind of just want to go over like as much content because
Yes,
I feel like
totally.
I'm just confused.
Yes.
So can you just go to like the beginning, like literally like page 2 of the first week?
This is
Like it's under the summary of first semester reactions useful in synthesis. It's like
okay.
literally the
I don't.
first page.
Yes, let me open up my own gap notes to make sure. I'll just follow along. Okay, summary of the first semester synthesis. Yes.
Yeah,
Okay.
so not the top part, but the synthesis of alcohols
Yep,
section.
that's
Yeah,
right here. I do have them both in here. Yep, right
so
here.
I just want to make sure. So for the second example, or no, actually, let's just start with the first one. So for the first one, I get when you have water, you're just gonna have hydrogen and the hydroxyl um added. But the H2SO4, I just want to make sure that is like that doesn't affect anything, right? That's just
That's
like
just a
a
catalyst. Yeah, it's just a
okay.
catalyst that helps remember. Because just quickly to remember what it looks like. Let me do it like this because everyone, you know. So and then it's able to be deprotonated, so it will, it'll donate its hydrogen somewhere, and then it'll steal something somewhere else. Those are backwards, but
Oh yeah, right.
you know,
I remember.
yeah.
Okay, so then, but then for the second one, um,
Mhm.
can you explain? So okay, so the top portion with the mercury, um,
Yep.
that is the regular Markovnikov, adding the same two groups, the hydrogen and the hydroxyl. But then
Hmm.
for the second part, for the sodium, whatever that is,
Yeah, sodium boron, whatever. Yeah.
can you
Mhm.
explain? Like, I don't know what that does. So, or
Didn't
like, what
we?
the
Yeah, so I thought they were just talking about this again, or is this a different one? Um, So let me just double check. I actually might not have it in. Oh yeah, no, I do. Alcohols.
or
Where
maybe the function of it, is it the fact that it will dissociate and the
it's
um
here. Yeah,
what
so it's this stuff right here. So this is just all a part of it. This is how you get. So remember, this is part of the mechanisms that like you don't necessarily have to know. Um, they don't expect you to know how this mechanism works. They just expect you to know that those two go hand in hand to create that um to create uh the product on the other side. I'm just trying to see alkenes.
how do you know the difference again between if something's going to go via radical bromination or if it's going to go via cation intermediates?
Radical bromination always will have H nu.
Oh, the light.
Yeah, the light energy.
Okay, okay, right.
Yeah, always. They'll always be H nu. Let me see. I'm trying to see. Maybe I just don't have an example of it in here, but yeah. So these are like this is just like your second step. I can't remember the exact mechanism of how it works, but it's basically like the hydrogen is donated to like work in the whole situation. It's a part of that whole mechanism. Like this is all one mechanism that you need in order to create your product. So you're always going to have that sodium borohydride or whatever it's called.
Mm-hmm. Okay, and then still on that same page. So wait,
Yep.
can you
Yep.
explain again? I'm still struggling with this. I don't know why. Okay, for
With
the
alcohol.
second, yeah, the alcohol part. On the second example and the third, it was said to be not stereo-specific, you get a racemic mixture.
Mm-hmm.
Like, I don't know what's different about those two as compared to number one, which is not getting a racemic mixture. Can you just like explain that to me again?
Number one.
Like, do you see how I guess she didn't write it, but she spoke it in the video. She said
Are you talking
this,
about this reaction or sorry, are you talking about this reaction here?
yeah, so that one was not, that one you did not get a racemic mixture, but the second and third you did. And I don't know, like,
Did she
oh, because
say,
there's no chiral center.
yeah, did she say specifically like that there it is not racemic? Is that
Um,
what she
well,
said? Or
she just didn't say anything for number
yeah,
one, but
I
for
think
number two and
probably
three,
the
she said.
reason why is that like in general is like we are not going to use this because you get this cation intermediate. So like that's why it says that's why she said like don't use the Bronsted acid catalyst, which is this right here, so that you don't get the cation intermediates.
Wait, how do you have those completed notes?
Well, because I'm awesome. No. No, because I'm allowed to view things that you guys aren't.
Oh, okay, I see, I see.
Yeah.
Okay, okay,
Because I'm
okay, wait,
special. No.
I know, now I get it, you so are.
Yeah.
Yeah, okay, chiral carbons for the second one, that's what I always forget. Okay,
Yeah.
okay, good. And then, okay, yeah, and so then the last one is the first degree, or whatever you call it, the
Yeah.
primary. And
Primary halide.
so then that's how, okay, so then that's how you know it's SN2. Because I'm gonna get to questions also. I couldn't figure out on the test what how to figure out which one it was.
S
Like I
SN2
knew,
versus.
yeah,
You
like
don't remember my cheat sheet?
no, I do, but like there was like an example where it was a tertiary, so
Yeah,
I
that
knew
would
it
never
was
be
an
SN2. Yeah.
SN2, but then how do you know like the difference between SN1, E1?
I know. I was just gonna say, to be honest, I struggled a lot with knowing the difference between SN1 and E1. That's a tough one because obviously, first of all, look at your solvent. Is it protic or aprotic? Is there a
But they
hydrogen that's
didn't,
going
I
to
don't think they
interact?
told you.
How are you supposed to do it then? What do you mean?
I don't
What?
know. I was really, confused.
So funny.
That's fine. It's
Yeah,
fine.
because you have, I mean, if I guess maybe if they gave you like the reagents and the products, maybe then you could try to figure out like, and then they give you like, some options. You could try to figure out what would be because that's true. You will try to like, um, assume, your reagents. So
Wait, can I just ask one more thing on the
yeah,
same page?
you can ask all the things.
Okay, so yeah, so for the third example, when they have the like OH and then they have the H2O2. So
Yeah.
if you look at the product, it's anti-Markovnikov.
Yep.
But my question um, is it anti-Markovnikov due to the fact that I thought the BH3 thing made anti-Markovnikov, but then isn't the step two a peroxide? And I thought
Hmm.
that also made so like it's anti-Markovnikov due to which one, or is it
The
both of them?
peroxide.
Okay, okay, okay.
It's anti-mark. It's like peroxide is what makes it anti-carbon because you'll see, in another set of reagent reviews, reactant synthesis reviews, you can see that there's all these, there's a handful of like ROR, H2O2, all of those are always anti-Markovnikov.
Okay. 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 And then if we can just like go through like in order for the 1.3, the synthesis of dibromides.
Yeah.
How do you know that the bromines are going to be replacing the hydrogens? Like, I just don't know how you know what's being substituted for what.
Okay, so the addition reaction, the synthesis of, let me see, anti-addition. So another addition reaction to an alkene that is required for further synthesis of alkenes later. So what you're asking is, how do you know that the bromines are going on the hydrogen across the alkene? Is that what you're saying?
Yep. Rather than like the phenyl or whatever.
Yeah, rather than replacing those. So if we were to draw this out.
Is it because they're the easiest accessible?
Yeah, they're gonna be, you're gonna be a phenyl group is this here. Yeah, otherwise you're gonna have this, right? So this is what we've got our phenyl groups on the same side. That's a horrible phenyl group, but hopefully you can, and then we have our hydrogens, right? Which, I mean, we're not drawing them in, so, but let's just say we do, right? So when we do our, you're going to remember the, let me see, where's our reactions? Remember the, what is my reaction summary? Oh, here's a good, oh no, these are with, oh, here it is, literally right here, right? So what you have is you have these here, and here's the mechanism too. So you have the electrons from the bromine that are coming in. Wait, did I say that? There is no hydrogens here. Why did I even draw those on there? Because those are our 4 bonds. Yeah, so you're breaking these off here.
Yeah, that's okay. Then I just read it wrong.
And then you have, yeah, and then because remember we have this here, Br, right? And then so this 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, right? And then we attach this here, and then we would have, what we would end up having is we would have this cation here, right? And we would have our stereochemistry.
Wait, but then why? I see the mistake I made. And then when it says no possibility of cis trans isomers, how do you know that? Or like,
where are you reading? Let me see. This is anti-addition. Oh, even though there is no in this reaction, we still need. Oh, so what this is saying? Oh, how do we know that there's no? Oh, I get what you're saying. Like, why do we have to draw the wedge and dash? Like, if there's not going to be any cis or tran, like, how come
no,
we
I
have
just
to
mean,
like?
yeah, but like, how do you know there's no cis and trans?
Oh, I would assume that this has to do with the way in which these have to attach. Because it's always anti-addition, which means that they always have to come on from opposite sides. So like you're not, remember like cis and trans isomer is like if you have your bromines both on the same side, that would be cis.
Yes.
So you're not going to have like, there's not going to be some, when it's saying like cis/trans isomers, that means that like it's always going to be this. it's never like it's always going to be trans, so to speak, right? Like it's always going to be that. So you're not going to have like, you can't have an isomer that would be cis because they
Okay,
can't,
so
they're
that's,
anti-addition. They have to come on from different sides. So
yes.
that's why there's no isomers. What it's saying is there's no isomers. So you're not going to have the same molecule in a different formation of an isomer, because that's what isomers are, right? It's the same molecule in a different formation. So you're not going to have that. So that's why it's saying like there aren't any possible cis trans isomers because the formation always has to be the same. But because there's four, because we have, you know, 4 bonds on this carbon, we still have to draw the wedge and dash to represent their stereochemistry.
Mm-hmm.
That's what it means. Because otherwise you would draw this, and that's not technically correct. You know, it is, but it's, you know, it's not, because and we, you know, you've got your chiral centers there.
Right. Okay, okay.
Does that make sense?
I
It's not
see,
necessarily
yes.
like, oh, we wouldn't have cis or we wouldn't have trans. That's like a whole that's a whole a cis trans isomer. That's like a whole concept right there. It's
Yeah,
always
I
going to
see.
be trans. There's no such thing as cis.
Okay, okay, got it. Let's see. Um, okay, I think I'm good. I'm just making sure there's nothing else on that page.
And then we have synthesis of alkenes. You got that.
Yeah, I'm fine with that. I'm fine with the SN2.
SN2. And we
Um,
have alkenes elimination of alkyl bromides using E2, strong bases.
yeah, wait,
CHF
so
and
for this,
anti-CHF. Yeah.
yeah, for this one, that one you just read.
Yep.
So, so how do you know that you're trying to avoid, so you're trying to avoid SN2 due to the fact that it's a bulky base,
No,
correct?
you're using a bulky base to avoid SN2.
Yeah, so why are you making the decision to avoid SN2?
SN2, remember we have substitution versus like elimination. Elimination is creating an alkene versus substitution is just substituting
Right.
your halide.
Okay, right. Okay, yeah, yeah, yeah.
So especially in
Okay.
this case, this is a second degree. SN2 will react. It might be slow, but it'll still react, right? So if we
Mm-hmm.
want, because think of it this way, when it comes to synthesis of whatever you're trying to make, right? If you're trying to synthesize a product and you have, remember, this is on like a subatomic level, right? And you have a way to do something where you can create either, nothing's going to be 100, but for the sake of this conversation, you can either have a 100% yield or you can have a 70% yield, because 30% will yield another product, right? The other yield would be whatever it was that you were trying to add. Let's just say this, an alcohol, right? Whatever it was, right? If you have 70% this major, right? Versus 30% this minor, right? But if you use this, you just get 100% this, and you're trying to create a product, do an experiment, make a medicine, whatever it is, like which one are you going to choose? Right? You're going to choose the one that maximizes the product that you need, right?
Mm-hmm.
So that's why we choose to do things in certain ways. Now, there's a lot of reactions where you're going to get both. And that's why, and you see in the lab, that's why you have percent yields, right? Or, you know, recovery yields. No, recovery is like, that's more like purifying your product, but percent yields, right? From your reagents to your products, to your crude product, whatever that is, you see a percent yield of like whatever it is, 10%, 50%, 80%, because you might have byproducts and side products, right? Byproducts are things that you have to have in the reaction. Like if you're, you know, eliminating water, if you're, you know, doing a dehydration reaction, then you're going to have your your product plus H2O. This is your byproduct. You'll always have that. But you don't want any side products because that waste, this would be a side product. This is a side reaction that does things differently. You don't want that because you're going to like waste your reagents. You know what I mean? You're kind of like wasting your time when you could maximize your yields. So
Right.
when they're asking you to do these synthesis problems, there may be more than one way to do it, right? But the idea behind it is what would maximize your yield in this for this product.
Mm-hmm. Okay. Okay. And then yeah, so I'm continuing for the synthesis of alkenes from alcohol. I'm fine with the water as a leaving group. I think. Yeah. So, and then they're trying to drive home the point, protonating oxygen to turn it from a poor leaving group into a good leaving group. So that's trying to get water to be the leaving group.
Yep. Because
Okay.
OH is not a good leaving group.
So on the top of page like 5, for example, when they're when you have that like 1, 2, 3, what is that? So a butane or whatever that is with the hydroxyl. Yeah, so this is like, is this like an SN2 of like substituting the, or wait, no. Oh, no, wait, this is just protonation. Yeah, okay, wait. So then how do you know? So when you look at this, for example, how do you know that this is just a regular protonation? Oh, because I know. No, I know. It's because you told me already that HBr is for alkenes, right? So you're not trying to like you're not doing like, wait, no, is this an SN2?
Well, the HBr isn't, but the next portion will be. You're just
Because I
protonating
thought
first.
because I thought we said that the HBr, when we were going over that test question, that like the HBr couldn't be the answer because it's only for the alkenes. But then in this instance, there's the SN2 reaction HBr, but there's no alkene.
So in this case, though, we're trying to, we literally have an alcohol that we want to leave, right? So this is asking us to create, if we look at this, right? So here's some right here, right? So we have HBr and we have OH, right? So this is a a representation basically. Remember that we have these like elimination reactions, our whatever reactions, right? Where we eliminate HBr and so we end up with this double bond, right? We end up with the alkene. So in the same way, we're trying to do the same thing with our alcohol, right? So we have a hydrogen and we have our OH. We want to kind of do the same thing. I don't know why I keep saying that. So it can be a good leaving group, but it has to, you have to make the alcohol into a water for it to leave, right? And so that's why we use this, we can't use this, for example, right? Because bromine's not going to, a bromine ion on its own is not going to replace that because this, we talk about the difference between the like acidity levels, and acids, right? So this, on the other side of it, it's a poor leaving group because this is happier being an anion by itself than this is. So the reaction really is pushed in this direction. The equilibrium is over here. So this is why this is not, we can't do just a standard substitution reaction because it won't, these products aren't stable. They will react with each other and the equilibrium lies on this side, right? So what we have to do first is we have to protonate our alcohol, right? So we have to protonate it first. So we use HBr to protonate it because again, Br is happy to be an anion on its own. It's a great leaving group, right? It says it right here. Br is a great leaving group. So what we do is we protonate it and we turn it here we turn alcohol into a water And what'll end up happening is, you know, it will leave on its own, and, you know, bromine will come in, push it off, because alcohol is much happier to be on its own in this way, right?
Mhm.
And then that's how we get this substitution, right? SN2, we get this substitution of the bromine on this carbon, right? And water is a
Yes.
very good leaving group, right? So that's why. So we have to, now we're going to be looking at things of like, eventually you're going to get to reactions where you're going to be protonating and deprotonating a million times before you even get to like the reaction that you're trying to do, because you need to like, and this happens, right? And it's very weird to think about, because it's like, oh, well, how does it know? But it's just like, we're
So
looking at these things on a very like step-by-step basis, but all of this stuff happens like in an instant, right?
so all of the protonation and deprotonation is occurring simply to create a stable like leaving group. Like
Yeah,
that's
in this case, yes, we're trying to create a stable leaving group. Yes.
so it will keep occurring until that
Yeah, the equilibrium
happens.
will lie somewhere, yes, and it has to do with concentrations, right? But yes, yeah.
Okay.
Mhm.
Okay. Okay. I think yeah, okay, that's clear now. Okay. And then yeah, okay, so I should also already know this, but for E1 and E2, so so under water as a leaving group, elimination of alcohols, E1 and E2.
Yeah, I'm just gonna
It
highlight
says
this right here because this is a concept you want to remember, because you will see the protonation and deprotonation of things. This in particular a lot. So anyway, go ahead.
yes. Yeah, so it says like water can act as a leaving group in a standard E1 and or E2 mechanism. So the difference again is that E2 has like two participating groups and E1
Mm-hmm.
only has one. Like so when you're looking at this, for instance, you have a secondary carbon and you have the H2SO4.
Mm-hmm.
Is that telling you that it's, I don't know how that's telling you if it's E1 or E2. Oh, it's, I wait. Actually, I have to look at this sheet. I don't know. I don't know why I'm like so bad at this.
So in this case, it can be an E1 because we have a protic solvent and we're adding heat, right? So those are kind of like traditional E1 SN1 type reactants,
But
right?
I thought that like when they say like two groups participating, I thought that meant like the hydroxyl group is one group and then like the H2SO4 is another group. Is that
Well, what do you mean two groups participating? What do you see? Where do you tell me where you see that?
in OChem 1 in the like
Mm-hmm.
last chapter,
Mm-hmm.
they were differentiating SN2 from SN1 and E2 from E1 and they were saying
Mm-hmm.
like what does the 1 and the 2 mean in the title? And
Oh,
I think it was Dr. Pillai in the review sheet said E2 means that like you have two groups participating in the reaction, like E1 just means you have one. And I guess I'm not clear on like what that really means because don't you always have two? Like you have like a group on the molecule and then you have like a reagent that's reacting, or maybe I'm not counting them the proper way. I don't know.
um, so
Yeah, she says E2 is bimolecular.
yeah,
E1
bimolecular,
is
yeah,
unimolecular.
unimolecular.
What does that
So
mean exactly?
unimolecular means that the rate of the reaction depends only on the concentration of the substrate. As the concentration of the substrate increases, so does the rate. So in E2, it's second order. Um, E2 circulates at 1.5 to 4 times the concentration of E1. Oh wait, no. 2 atoms on adjacent carbons are removed or eliminated in order to obtain the product. The end result is a new alkene. That's just elimination in general. Let me see. The yields are lower in E1 versus E2. It has a unimolecular rate determining step. That's what it's talking about. So it depends on the concentration of the substrate and not necessarily the base. So it proceeds fastest when a more stable carbocation can be formed, does not require a strong base, and does not have any requirement for CH bond to be in a certain orientation. Okay, so whereas E2, you have to have a carbon, a carbon hydrogen bond near where your other eliminated group is, right? For us, we've been using halides, right? So bromine. So the next carbon over, somewhere has to have a hydrogen on it. Is not the case with E1. Remember, because we have carbocation and rearrangement.
Oh, and then it can rearrange.
Yeah,
Oh,
exactly.
okay. That's good.
Yeah.
All right, let me
Yeah.
write that before I forget.
E1 does also not require a strong base, but remember that we add heat to it, to help increase the reaction rate.
Okay, 1 second. Okay. Okay, yeah, that's good. Okay. Let's see. That's switching. Okay. Okay. Let's see
Yeah,
what
strong
else.
base is required in E2 that will allow the displacement of a polar leaving group. So your leaving group has to be polar. The stereochemistry, which would be HBr, for example. The stereochemistry of the hydrogen to be removed must be anti to the leaving group, which we also know that. The pair of electrons from the carbon-hydrogen bond donating into the antibonding orbital of the carbon leaving group bond, leading to a loss as the electrons. I might be getting too much into it, but
Okay. Yeah, I think I'm good with
there
that.
is a website called Master Organic Chemistry that's really amazing, that I use kind of often. So
Okay, I'm writing it down.
yeah, I
Master
really,
Organic Chemistry.
yeah, Master Organic Chemistry. Yep, exactly. As in like master
Okay.
the concept. Okay.
Okay. Yeah, let's see. Then okay, so then they're making some distinction on still on page 5 at the bottom. They're making a distinction. Why does the alcohol make an alkene plus water when previously we learned that water plus alkene gives an alcohol?
Yeah, why does
So,
alcohol make an alkene and water? When we learned that water and an alkene gives an alcohol. Okay, yeah, so we previously learned that the alkene plus water gives us the alcohol. So it's an addition of water. The addition reaction goes because the weaker pi bond is converted into a stronger sigma bond, which we know the reagents and conditions have a larger quantity of water and a smaller quantity of sulfuric acid. The reason for this is because we need the bonds to interact with water versus the sulfuric acid because they also will act as a donates the proton Lewis base, Bronsted base.
wait,
No,
so does
Bronsted
the
acid. Sorry,
sulfuric acid, I thought, I'm confused. Does it protonate or does it deprotonate?
it can do both. So remember what sulfuric acid looks like.
Yeah, because like the hydrogen on the end it leaves, I think it doesn't it leave in the beginning, so it protonates in the beginning and then it
Yeah,
deprotonates in the end.
yeah, that's what I'm saying. It
Okay.
can, like any good catalyst, it regenerates for one, and for two, yeah, it can do both. It can protonate and deprotonate. So it's a good Bronsted acid, which is why we want the concentration to be lower than than our water, because we want the reaction to go via the water, right? Because we're trying to add the alcohol.
Yeah.
So, okay, so this is what we now learned, is that we eliminate the water to make the alkene, but we have a higher concentration of the, I guess, where is this? So this is further down, I guess. Okay, I just don't have it here in the gap notes, but, or on my iPad, but yeah, so then what it's saying basically now is we're using a higher concentration of sulfuric acid so that we protonate, deprotonate, we protonate the alcohol and it becomes a good leaving group, and then we can pick up that hydrogen onto the like what happens is, let me just draw out this example here in the right. So what happens is we, we've got these, right? But we pick up this, which then becomes water, right? And then this becomes a good leaving group. But now because this, and also, sorry, these are here like this, but now this has, this one right here has a negative charge to it, and it wants to regenerate itself. So then it picks up this, and these go here because this is here, right? And then that's how we get this. Make sense?
Yeah. Yeah.
So
But
then
I just
this is
have,
regenerated, and this is
yeah,
our plus H2O.
yeah, I follow that. I just have a one question though. Like on that
Yeah.
mechanism
Mhm.
they drew, it is saying that it's a one or a primary alcohol, right? And I understand
On this one up here,
uh
or
oh
what one?
um it just is under one of the examples on page 6. It says example primary alcohol E2 elimination with rearrangement.
Yes, yes. I just don't have, yes. These are on the next page, but yeah, go ahead.
Yeah, so and then you see the mechanism, and in the second to last step, you have a carbocation.
Uh-huh.
Um, and that, but if you read the paragraph, it says with a primary alcohol, the mechanism must be E2. Formation of a primary carbocation it can't occur. But
Yes.
then in the second to last step, it looks like there is a carbo. Oh, is it because
It's
when they
tertiary.
say primary,
It can't
oh,
be a primary carbocation. This,
oh, so it's
remember,
not saying like you can't start with a primary because I got confused because it's starting with a primary
no, it's
alcohol.
just saying like this will never occur. What'll happen is this hydrogen will pop over here and this will become a double bond.
Yeah, got
Like
it.
you're not
Okay,
gonna
got
have
it.
a primary carbocation. It just won't happen.
Got it. I see.
It's not stable. So as the
Oh,
oxygen leaves, the hydrogen hops on to create that double bond, right? And then what we end up doing is we get the hydrogen back from, we take a hydrogen again from the concentrated, sulfuric acid, and then we create that carbocation down here, and then that reacts with, you know, another hydrogen over here, which moves it here.
I see. Okay, okay, okay. Let's see what else. There's so much to go over. This is like,
Yeah, there's a lot of content, I know.
I feel like the first week there was so much. Like,
Yeah. Yeah, this week wasn't as bad as I thought, although, the one of the chapters was like 18 pages, but I thought it looks like there was a lot more on there than there actually was. So,
yeah.
um, yeah, okay, so these are alcohols, first degree and second degree. You have your multi-step synthesis. This is when we start talking about like putting it all together.
Mm-hmm. Okay. And then, yeah, so just real quick, so on page 7, you've kind of already explained this to me, but I just want to make sure.
Mhm.
When you have it's like the hexane, and then you just have the hydroxyl with the salt or reagent or
Yeah, so you
whatever.
go from here to here.
Yeah, but how do you know that you're
I
gonna
know.
form a
Great
molecule
question.
that is just not having any hydroxide? Like, how do you
Uh,
know you're like some, you know how sometimes you like are doing substitution or whatnot, and then sometimes you just end up with a molecule that has just double bond. Like, how do you differentiate it at that point? I don't,
say the question again. So I want to make sure I'm understanding what you mean.
yeah, so I just want to like, so in the reagent or the reactant, you have
Mm-hmm.
the ring and you have the hydroxyl.
Mm-hmm.
And then in the product, you just have a ring with a double bond.
Mm-hmm.
Like, like this is just is this just an example of what we've been discussing, protonation and deprotonation to get water to be a leaving group? That's it.
Mm-hmm. Mm-hmm.
Okay.
Mm-hmm.
So in the
Well, to
prior
get the
example,
alcohol, to get the alcohol to be the leaving group, we have to
yeah,
turn
yeah,
the alcohol into water so that it
yes,
becomes the leaving group. Yes, this is all of these examples are just examples of like we're now moving backwards, like how we had um water, we added water across the double bond to create an alcohol. Now we're seeing, which I mean, I guess it was before this, but yeah, so before um we had a double bond and we were adding water across it to create alcohol. Now we're seeing the opposite of that. How do we have an alcohol and turn it into a double bond? So this is just the reverse of that reaction essentially. And the the difference is the concentration of sulfuric acid and the presence of water, right? Because in
right,
this, obviously we're trying to create water. We're trying to make water the leaving group because these are all plus H2O plus H2O, right? So we need low concentration, low to zero, right? Concentration of H2O and high concentrations of acid because we need this product to go in this reaction. Remember the concentration gradients,
yeah. No,
right?
yeah.
Yeah.
It's just the reason why I was confused is because back from page 2, like, remember when we had water and then the H2SO4, and you just said, oh yeah, it's just the catalyst. And if you
Yes.
look at the product there, the product contains the hydroxyl and the hydrogen, and it's almost as though like the H2SO4 is like kind of not like, I don't know, like it's not like it's almost doing the reverse. Like
It
in the
is. But that's exactly right. That's old review. This is old review stuff. Remember, we have water, and we've got a little bit here, got a little bit of acid to help catalyze the reaction
yeah,
so that
okay.
we get the alcohol.
Yeah,
Again,
I
we're
see.
not using this because we have a carbocation rearrangement. We're not doing this, right? But
Mhm.
but right,
Yeah,
this is because we have high concentration of water and low concentration of acid, so that we get this, that we need this in order to get this stuff to react, because this water is not going to add to this alkene for no reason, right?
right.
So
Yeah,
we need that in order to, that's why it's a catalyst. It helps the reaction go, right?
yeah,
Versus down here, we have high concentrations of H2O and zero, right? Or very low concentrations of water, because this is going to get deprotonated onto here to make it a leaving group.
right. Okay. Yeah, I see. And then for the further stuff, the next one is the multi-step synthesis. Can you explain the strategy on how to know like
Yeah.
like I just yeah.
Oh, the bane of my existence. I know. Practice, 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 practice. That is my best suggestion, to be honest. It's sad to say. It is hard to necessarily know this. We're starting to get into multi-step synthesis. We're going to be getting into reverse synthesis, right? And that's why we start talking about in this next page here, like synthons, right? Is like if we break it apart, how do we know? This is going to help us in reverse, right? But yes, first, okay, we talk about this. We want to say, okay, if this is our product, how do we, I mean, sorry, if this is our reactant, or yeah, if these are our reactants and this is our product, how do we get there, right? So, what's the difference? The difference is this double bond. Well, how do we make a double bond there? Like, what do we do to make, what do we know to do to make a double bond, right? Like, so how do you, what do you know in your head about how to make a double bond?
Yeah, so you got to get rid of a very stable group so it can stand alone. So you basically add a halide.
Yeah, exactly. It's we remove a brom, a halide, yeah. So in order to do that, now we have to add. So where would we add? So in this case, right? So let's draw it out. And I know you can, obviously like see these answers here, but um and here, we can also, like we just discussed, right? We can make double bonds from the removing of alcohols, but in this case, they're like, it's not, we don't we don't have a way to add an alcohol right now without a double bond, right?
Mm-hmm.
So that's why using this synthesis doesn't work right now. So, if we need our double bond to be here, right? But we have this and we know we need to add a halide somewhere. What are our options to add a halide, right? So it has to be touching this double bond in some way. So we would need it either here or we would need it here, right? Because you in order to create it, in order to create it in that space, unless there's like a carbocation rearrangement, right? We have to have it there or there, right?
Mm-hmm.
So, how do you put a bromine on that? You know, so you can, if you've got nothing here, you can do, oops, you'd have to, in order to put a bromine, remember we talked about this in the beginning, right? Is this, and just, it's best just to say NBS, because then you don't have to know the difference, right? And then you've got your
Mm-hmm.
bromine there. Well, okay, that's good. So now we know how to get a bromine, at least on that space. Well, now what is it that we have to do to get that bromine to leave in order to create that double bond? Well, it has to, what we know to make a double bond from a bromine, from a bromide leaving group or a halide leaving group, is it has to, by elimination, right? So that's what we know. We know like elimination removes the bromine and creates a double bond. So, and like we just said, it has to be the adjacent carbon has to have a hydrogen to leave with it. Well, what are our two choices? We have a hydrogen here and we have a hydrogen here, right? And so if we had a hydrogen here, our double bond would be here. And, if we had a hydrogen here, or whoops, if we had a hydrogen here, our double bond would be here. Obviously, our double bond target is this. Well, what are the two, kind of reactions that we know to eliminate HBr, right? And so we have KT-butyl and NaOMe are two just kind of classic examples. Well, what's the difference? KT-butyl is going to give you that anti-Markovnikov or anti-Zaitsev, excuse me, because it's a bulky base. So it can't get in right here. So it's going to take this route. So we're going to end up with this one. Well, that's not right. So we know it can't be this one. So it's going to have to be NaOMe. So that way we can get this double bond on the ring, right? And
Mm-hmm.
this is a very small This is a very small, this is a 2-step. Eventually you'll get to like 6 and you'll want to pull your hair out, but baby steps, baby steps. I used to always ask Dr. Ply, like, we don't have to do this many steps on the exam, right? And she would just like smile. I'm like, oh God. She'd be like explaining answers. I'm like, oh my God. So anyway, so that's something that we have 2 very similar looking molecules, so it makes it a little bit easy. We know there's only really going to be one or a couple steps, right? But that's how you think about it. That's how you think about it. Like, okay, if I have this and I want to get to this, what's the difference between the 2? Well, in this case, it's just an alkene, right? And you know how to make an alkene by some sort of elimination reaction, right? So what addition, what do you eliminate to get the alkene, right? And as you said, a halide. And how do we add a halide to a carbon,
Yeah.
Photobromination, right?
Yeah.
Without having an alkene already, right? Photobromination. Does that make sense?
No, yeah, it does. Yeah, I was like looking at, I don't know, the multi-step ones, they make sense when you look at them. They just don't necessarily come when you have to produce.
Yeah, no, I know, I get it. I get it. Like, okay.
So you just like start at the target and kind of go one step back at a time and just think of like,
yeah, we're gonna do this one right here.
And it's like most common for your intermediates to be like brominated or something like that. Like that's like the trend.
Maybe right now, yeah. Let me see. Let's see, this is the product, right?
Yeah, exactly.
Yeah, so I'm sure you already have this filled out, but don't look at your notes and just try to, get your reaction summary out, but don't look at your notes, right? So what are some like, what's the difference between the 2?
Yeah, so bromine.
Yeah, this bromine right here. So we're just adding a bromine. Well,
right.
What are our options?
Yeah, so don't you use either like the NBS or the well actually
you could use both. You could use either because there's no alkene already. So, but the reason why I keep saying this just to use NBS is because then you don't have to remember the difference. And no matter how the molecule looks, if you use NBS, you can just put it right on that most substituted radical, right?
But the thing is that the bromine is being added to a location that isn't the most substituted carbon. So it's like,
so what does that mean? More than one step, right?
yeah, does that mean that you would use yeah, but does that mean that you would use a BR2 or an MBS, or would you use a HBr and do a peroxide to try to like get that position?
With HBr and a peroxide,
Because it would add an anti-Markovnikov, right?
But the only way to get it, when you have HBr, you're adding it to an alkene.
Okay, so then you need an alkene as the intermediate, right?
Maybe. How do you get an alkene?
How do you get an alkene?
Well,
I don't know.
to do anything with this reactant, what do you have to do? You got to put something on it, right? So what are your options so far that you know?
I think you're putting on a bromine because that's just the trend.
Yeah, it's the only thing you really know. You only know how to put on a halide at this point, right? So
So you can put on a halide too, using like, using either diatomic bromine or NBS, given there's no double bond.
Yeah. And I'm just gonna do NBS H nu, just for the sake of, So now,
And it will add it to the most substituted
yep,
location. Yes. And then
now what?
now we want to eliminate bromine to form a double bond.
Mm-hmm.
So let me think.
So
Oh,
what
wait.
are our two options for eliminating? What are our two, what I'm trying to say is like, um, if you're going to eliminate it to create, what are the two options for this bromine to create a double bond? So remember, it has to be to an adjacent carbon, right?
Yeah.
So these are our three options. And truth be told, blue and green are kind of the same, right? But just for the sake of the drawing, right? So
So it's a tertiary carbon.
yeah, so we have either an option to make a double bond either here, right? One of the two. I'm just
Yeah,
drawing them
so
out
you
together.
want the second one, of course, because
Or you
you
have
want
one here.
you don't want that.
Right. So if you don't want this orange bond, what reagent would you need in order to make the orange bond?
To make the orange bond, which is less substituted, right? Or that's
Yeah.
anti-CHF.
Yeah. So
You
what would
would
be the
want,
reagent that you would use for anti-states?
yeah, it is. Wait, hold on. It's either the bulky or not bulky, but don't help me.
Well, before you even look, think about it for a second. Bulky or non-bulky?
I think it's bulky makes anti because there's like bulky is large and then anti is like there's the least amount of things around it.
Yeah, steric hindrance, right? So you just figured it out
Right.
without even like just thinking about what you said, you figured it out, right?
So you want to have a non-bulky base.
Yes. Okay, so now what's an example of a non-bulky base?
Um like the methane thing. I don't know.
Yeah, like NaOMe, right? Is that what you mean?
Yeah.
Oh, no, that's not what you mean, huh?
No, that is, I just don't know what it
Oh,
is.
okay, yeah, yeah, NaOMe, yeah. Okay, cool. So then you have NaOMe, and what would that,
That would
where would,
form the double bond where the blue is adjacent to the green dot.
yeah, yeah. So let me get my
So
colors back. There we
just
go.
a
Okay, so
question. Wait,
yeah,
so whenever you're trying to like eliminate a bromine, like whenever you're trying to go from like something like step 2 to something that like step 3 that has no like other substituents like just carbon, hydrogen, and a double bond, are you
mm-hmm.
always looking to use either like a bulky or non-bulky base, or you can use the H2SO4 though, right? From like that last example we were discussing. If you want to like eliminate if it's a alcohol, if it's like a hydroxide, you can use that. Like those are your options.
Yeah, yeah, yeah. Anything that you've learned, you like those everything's free game, right? So the H2SO, the sulfuric acid, that is specifically for your alcohols, right? Versus like these ones are for your halides because halides are good leaving groups.
And so
Or
now
halides are good, yeah, go ahead.
so now you, the only option, right, is to use a hydrobromic acid with a peroxide due to the fact that the bromine is being added anti-Markovnikov.
So good. See what you just did there? Boom.
Miracles do happen.
They do, right? It seems scary at first. And if you have your reactions, that's why it's like do your practice problems with the reaction sheet. Literally use your reaction sheet as a reference every single day until you hit the exams, right? Like, because the more that you do it, the more you just, as soon as you get stuck, look, figure it out, and move on. Don't try to guess. You're not going to be able to guess. This is new material to you. You don't know what the answer is. Sometimes it's not, if you can figure it out deductively, like you did with bulky versus non-bulky, great. But like, don't kill yourself trying to like remember what the reaction is. Like, just look. So that way you start building those neural pathways, right? Of like, oh yeah, it's this right away, you know?
Yeah.
Yeah.
Okay. All
Good
right.
job.
I think progress is being made.
Yes, progress is being made. Look, and here we are, right? And this is like an example of like how you can kind of go backwards a little bit too, right? Is you can look like, okay, so, you know, with this, for example, right? If you started here and you knew that you needed to get a double bond on there, like what are your options? Like these are your three options, 1, 2, and 3. Right. And so, or if you, excuse me, not if you need to get a double bond on there, if you need to get a bromine on there, like how do you get a bromine here? Right. And so if we're moving backwards, if we're moving in this direction, right. Well, you know, NBS and HB is HNU is not going to put the bromine there. So that's why we're not going to do this. And then if you had an alkene, the other option is if you had an alkene and you added a bromine, if you just do HBr, it's going to add to this one. So that's why it can't be this one. And our only other option is this, right? And so that's an example of like how you start to think about retrosynthesis is okay, well, if I didn't have this bromine here and I needed to add it, what are my options? Well, my options are either photobromination or adding across an alkene, right?
Mhm.
So those are just some, you know, ways to think about it. And then, you know, you figure out like, oh, okay, well, if I did photobromination, it definitely wouldn't go there. So, you know, and if I added it across an alkene, I have to do an anti-Markovnikov.
Right. Okay. Okay. Yeah, I sure wish I went to the Wednesday office hour right about now.
You know, I post them. You could have watched them.
No, I get like an hour and whatever of like just
Yeah.
like it's so beautiful.
Yeah, no, it is. It's helpful. It's helpful to, you know, it's like taking classes online or no, you know, it's not easy. It's not all cracked up to be.
Yep.
Um, we can do about 15 more minutes. What do you want to cover?
No, it's okay. It's okay. If you have to go, you've already given me so much time. It's really fine.
No, you're fine.
I just have
I'll do
to.
my son's sleeping. If you want to get off, that's fine. But my son's sleeping, so I'm not. You know, we're good. I can do about 15 more minutes if you wanted to cover something
Okay.
else because we kind of covered like old material. We haven't really covered much for like this week, and so I just want to make sure you're, you know.
I know. I know. I guess, yeah, from this week, I started watching the video, so let me see. I do
And
have
even if
questions.
it's not, I know it's still early in the week, so if you know, we can still cover stuff from last week too if you have questions. I'm sure other people do too.
Yeah,
So
I mean, at the end of the day, I don't really care because I need to know all of it. So it's like I just need to I don't know what I'm just saying. Like, yeah, let me pull up what I did for this week. Because I did have questions.
let me see. And this is our reaction summary from last time. This is our reaction summary from OChem 1, right? This is OChem 1 stuff. OChem 1, right? And then we see some of this kind of newer material.
Yeah,
Now we're
so
starting to work with alkynes. This was last week, I believe. Most of this stuff you started to cover also this week as well. The acetylide anions, right?
honestly, I think I'm just gonna keep going week one because
Okay.
I still have Wednesday for the other stuff and it all builds on each other.
Yeah, no, it does. It does. It's definitely helpful.
Okay, so for the synthon, that's where
Yes.
we're at right now. So
Yes.
that so in the videos, they never really defined what a synthon is.
Yeah, I
Um,
know. They're just like,
what
things that we
what is
use to
it?
help conceptualize it.
Okay,
Like
So,
it's like, think about synthons as like synthetic, right? Like we're synthesizing, right? So it's just a way to conceptualize where it would come from. Like how could we potentially get to where we are now?
but how do you know where to break, like what bond
You
you're
don't,
breaking?
right? That's why you got to look at it. You don't necessarily know. And there might be more than one option, right? But so the biggest thing that they say is like, can you bottle it? Like, does it make sense, right? And so a lot of the times you're going to go through and you're going to break both the bonds and see which one, you know, where would be the most likely, right, to disconnect from. Right. So like, so in this case, we have two options. We can either cut it off here. You know, we're not going to be cutting the, obviously the ring, right? So we can cut it here, we can cut it here. Well, you know, is it likely that we're going to have some sort of anion here? Probably not. You know, um,
So
you know,
like
you're not
what
going to
are
have
you
like
trying, like yeah,
here.
but like when you cut it, so what is the motivation? Like what are you trying to achieve? Like I'm not clear on that.
This is so that you can, this is in order to start to do your synthesis, right? Like if we look, putting this all together, this is our final product, right? This is what
Right?
we started with. So this is a retrosynthesis strategy. So from our final product, we start creating synthons to try to figure out how we got here. How did we get here? Well, there's a couple different ways that we could look at it. So most likely, right, we added this OCH, OME, right? Same thing, OME,
Okay.
remember? Right?
Yes.
So we look at this, here we are, OME, right? And we've done this before. We've added OMEs, right? So we're most likely going to do this. Well, this is your synthon, right? So this is like what needs to happen to connect the two, right? But what's your you know, synthetic equivalent, right?
Yeah, so
So
what
what
exactly, wait, sorry. The synthetic equivalent, I don't really understand like what that like
a synthetic
is.
equivalent is basically what is equivalent to this but would actually exist in real life. This is not going to exist in real life. We have a primary cation. It's not going to
Okay.
exist in real life. This, on the other hand, will exist in real life. And we can make that happen, right? This isn't, if we didn't have this bromine here, this is an anti-Markovnikov addition of an alkene,
Yes.
right? So we
Yes.
can make that happen. So that's what they're saying is like the synthon is like how is the raw material that we would need in order to create our final product. This is the raw material that needs to come together in order to create our final product over here, right? This is our final
Yeah.
product. And so in order to get that, we would need this and this to come together, right?
Mm-hmm.
So that's what our synthon is. But synthons don't necessarily, they can, but they don't necessarily exist in real life, right? So what is the synthetic equilibrium, equal equivalent? You know why is because I hear Dr. Pillai say it all the time, and she says equivalent, and because of her accent, and so every time I hear it in my head, I'm like, wait, but that's not how it's pronounced, and so I have a hard time because I always want to say it the way she says it because heard it so many times. So I want to say synthetic equivalent, but I'm like, it's synthetic equivalent. So anyway, your synthetic equivalent um, is going to be what would exist in real life. So hopefully that makes sense. So the synthon is just your way of conceptualizing how you would get to your final product, right?
Yeah, okay, I see.
And so in
Okay.
here we see that we have like we've got a couple options about like what would be if we were going to synthesize this product here. What are a couple options that we have? Well, you're going to cut it on either side of the oxygen, right? Because you need, you know, like you're not going to cut it here, right? Like you have to have some sort of like reactant somewhere, right? So
Yes.
anyway, so you're going to cut it on either side of the oxygen, and you're going to see like, okay, what are my two options? So if we disconnect B, we're gonna have, you know, a methyl, right?
Mhm.
Versus if we disconnect it here, we're going to have the OMe here, um, with our, I guess, T-butyl. Um, and so the
Yeah,
reason
so
why, yeah, go ahead.
sorry. No, I
No,
was
go
just
ahead.
gonna say, so it's I see like the pattern that I noticed was that like when you have the positive synthon, you add, or a lot of the times you add a halide like a bromine, and then when you have the negative synthon, you add like some like sodium, for example.
Yeah,
If
an ion, you know,
yeah,
to stabilize it. Yeah.
so like are
It's a
those
salt,
the
basically.
most common trends? And then wait, so because then and then like even though the sodium was like thrown in the picture now, the acetylide anion was
Hmm.
always being used to react with the newly formed, like what used to be the positive synthon. So the
Hmm.
like sodium isn't actually like
No, no,
bonding, it's just
no. Do you remember how ions work, like salts work, like that they're just they're their own things, right? Like this ion and this ion exist separately, but with within reason of
yeah,
each
they're like
other.
dissociated.
Yes, exactly. Yes, they exist. They're dissociated. They exist within the presence of each other for moral support, but they're not bonded.
Okay. And then does the so and then for the synthon stuff, um I feel like all of the examples have been SN2 with them. Is
Mm.
that common? Like, I don't know. I just didn't like because it's a synthesis reaction, is it going to be SN2? Because all the examples were, so I didn't know if that was like,
Well, I'm not exactly sure about that, but this specifically says how would you make the following molecules using an SN2 reaction? So they're telling you that you're going to be using SN2 for this
oh,
portion.
okay. Yeah, because then it says like SN2 reactions revisited, practice doing reactions in reverse. So I didn't know if there was like an
Yeah,
area where
it
focusing something.
might just be that they are asking you to do, because this is obviously a common synthesis like mechanism, right? And
Mhm,
it's something that you just learned, and so now they want you to basically to apply those principles, but in reverse, right? So like, how would you
mhm.
create, right? And so it's substitutions. That's why here, third degree halide, you're not going to get an SN2 because SN2 does not happen on third degree, right? So
Yes.
that's why this one is better, because you have to put, like you said, your, in order to make it real, your synthetic equivalent, um, you know, needs to be able to react. So this SN2 reaction can happen because this is a first degree
Yep. Okay.
versus this is a third degree, right?
Mhm.
Um, and kind of same thing here, right? So, um, we've got a first degree here. We would have a first degree bromide versus, oh God, I always get these. B is, yeah, if we cut it here, the bromide would be here. If we cut it here, yeah, the bromide would be here. Okay. Oh, I guess it's over here. I didn't even see that. But yeah. So so this would be second degree. So with SN2, you remember we have allylic or benzylic, right? And then we have first degree, second degree, and no third degree, right? So a first degree versus a second degree, like it'll go, but it's going to go faster if we do it here. And remember, we're trying to create, we want to know like what's going to be the fastest, what's going to give us the most yield. So that's typically your best answer is always going to be like what is either the fastest or would produce the most yield.
Yeah, I see. Okay. Yeah, every single time I call an office hours, it always makes everything so much more simple, you know? So, how
Well,
great.
that's from my previous experience of being beaten by organic chemistry. So
Wouldn't know it by listening to you.
Yeah. I got my butt handed to me in OChem too, I won't lie. I still
Well,
made an
I
A,
think
but I was like, I was nervous for a while. I'm like,
well, I think I'm like good. And then now I'm gonna like now I can just like cause like just focus on the remaining
yeah, the stuff for
portion.
this
Cause
week.
the no, yeah, cause like the 18-page thing was
All kinds.
also some of like it also was some of the material from this week. So I just have to like kind of look at that again. But it's not
Yeah.
I'm
Yeah,
only
yeah, no.
watching the whole video, so it's not bad.
Yeah, yeah, no, and like, at the end of the chapter was really just like it was giving you, we're practicing like, okay, if we want to get from here to here, like what are some things that we can do, right? And so we know these little reactions as we go. And so as you start getting more and more and more and more and more, right? It's not as easy to see because, there's more steps involved. So that's why they start talking about these synthons and the synthetic equivalents, because we need to start understanding like where some of these products are coming from and what some of the options are, right? Because maybe it's not so obvious because we're not necessarily ending with a halide or an alkene or an alcohol. We're ending with some of these like other types of products, and you'll also see where we start adding on, and where our product doesn't look anything like our reactant, right? And so that's why we start doing these things where we practice these synthons so that we can um look at the potential of um where these come from, because they
Mhm.
won't be as obvious. As the further along you go, the less obvious things will necessarily become from start to finish. But if you can start to break things down, you can make a few steps and then go back to your like old ways of like, oh yeah, well this reaction makes that and that reaction makes this, and it's a lot easier to do. But I
Mhm.
will say too, like with retrosynthesis is, they very much encourage you to do things backwards. That's the whole point of retrosynthesis, right? You start at the products and end up with the reactants. But I personally had to do a little bit of both to see. It was really hard to go entirely from one side to the other. Is like I had to give myself, the middle was usually what I did last, is what I guess what I'm trying to say. So um but it does become, as like what Dr. Austin was saying in the beginning of the videos in OChem 1, is that it is like a little bit of a puzzle, like Sudoku or something, is where you have to really kind of figure out like, okay, what are my options? Like, let me play around with this. And you might get halfway through a synthesis and realize that like that's not even going to work, and you've got to backtrack and like figure out, okay, well, what are some different options? And so my biggest advice is just like, do not fall behind on your reactions. Do not like lose practice or lose touch with what makes what happen. Um,
Yeah.
find a way to simplify it for yourself, and that, might be that like, you remember whatever if you have H new, it's like, photobromination. So you're going to add, right, to, the most substituted, right? Um, well, but if you have an alkene, right, then you want to make sure to use your NBS, because then, you'll do an allelic, right? But, and then, HBr, it's Markovnikov. Anything with peroxide, you're going to have this anti-Markovnikov addition, right? BR2 is always going to be a syn addition type situation, right? And then this is where we see again this, we're now doing a substitution of our bromine into an alcohol, right?
Yeah.
Same thing with this. This is going to be your Markovnikov version of adding water across an alkene, right? Um, let me see what else.
Just real quick, why is the it's like NH2 or whatever? It's some amine thing. Like it's like the solvent.
Yes.
Yeah, why does that add it was like I think it was Wait, there's something weird. Oh, hold on. Sorry.
Wait, is it?
What was
No,
that?
you're fine.
In this video, in the videos from this week, I like had just watched it, and oh my gosh, now I'm not gonna be able to find it. Whatever.
No, I think I have it
Find it.
here.
I'll just
Are
ask you
these
on the
ones
oh
any NH2?
yeah, like something got added. Yeah, okay, yeah, wait. Yeah, so how is there a bromine? Like, where is the bromine coming from?
Where are you
Do you see
looking?
where it's like it says a
Oh,
under SN2 reaction with alkyl halides and then the example and like there's
mhm.
like the triple bond and the hydrogen it that middle
Yeah.
section.
uh,
Yeah,
Um,
yeah, like right there, kind of where your no, like right above it.
up here.
Yeah. Do you see how like there's it's literally just all carbon and hydrogen. Then it says NaNH2, and then there's a bromine, but I don't know where the bromine comes from.
Yeah, that's just the reactant that they're using. That's how you're, because you'll have to see as you start to go, you'll have to, not only will you need a reactant, but you're also going to need to, because now we're getting into adding to our, right? And so addition of water, right? But now now we're getting into adding to our molecule, like, right? Like we're not just like for this one, for example, right? This is why we're using this, is like not only we're starting with this, which is CH3, right? CH, right? And what we end up with is CH3, CH2, CH3. So we've added on, we see that, and it's highlighted here, right? We see that we've added on here this CH2, CH3, right? So we've added
Yeah,
this part on.
but what
So
contributed to bromine?
this is, remember, our synthon, right? So if we have this, right, this
Oh,
is
so it
our,
just yeah, no, I know, but like where does it come from? Like it has to come from somewhere, right?
bear with me,
Sorry.
it's fine. Okay, this is our synthon.
Yes.
So what's our synthetic equivalent?
Yeah, but where does the bromine come from in order to even put it on the synthetic equivalent?
You have to make the synthetic equivalent. Remember, this is just, we're just making shit up, basically.
Oh,
Like you need, like this is the synthon, right? So what does this need to be? How do we stabilize this
yeah,
so that we
yeah,
can
yeah.
use it in a reaction?
Yeah, I got
The
it.
best
Okay.
way that we know how is to add a halide so that we can do a substitution reaction
Yes, understood.
or an
Okay.
elimination reaction or whatever. In this case, we're doing
Yes.
SM2, right? So in this case, we're doing SM2. But
Okay.
so we have to create, and that's what I was starting to say, is that you're going to see that we're using this, right? We're using as our first step of the reaction because we want to, so annoying. There we go. Right? Because we need to get rid of this hydrogen to create our synthon, right? So we have to somehow to go from here, one, all the way over, mother trucker, all the way over here to two, our final product, right? We need to somehow make this react with something, right? So we have to strip the hydrogen off, and we strip the hydrogen off by reacting with our new, now, favorite new mechanism, right? Of like, and then in order to add this two carbon chain, we need that, which is here, right? We need that in order to add to it. So, and we put the bromine on to stabilize it so that we can proceed with the reaction, right?
Yeah,
Well,
understood.
yeah, this is specifically for this because this is butane, right? But you get what I'm saying, like this one
Yeah.
here, right? So, but you see the notation is what I'm trying to say, is like this notation of like 1, 2, right? And so that's why we see this notation that we can literally go from this reaction, right, to this by just a simple notation of like 1, we do this, which is creates this, right? And then 2, our second reaction, you know. So you just add it on so that way you can actually make the synthesis happen.
Okay.
Yeah.
Thank you, Sarah.
You're welcome.
As always.
Anytime. Yes, no problem. Anytime. Happy to be of service. And I hope that everything goes well.